All right, we're going to be talking here about electron configurations and going a little bit more in depth in what the atom actually looks like. So we're going to start off with the question of what inspired the Bohr model of the atom. And so we know with the Bohr model of the atom, we have that nucleus and we have the rings going around it. And well, in fact, it looks like this here. All right. And so we know that this is the Bohr model. And we say, well, it kind of models after the solar system, right? With planets rotating around the sun. And a lot of discoveries in science are going to start off with this concept of using things we know to explain things we don't. And so this was a good explanation to start off with. So from the Bohr model, we had this thought that light can act as either a wave or a particle. When it's emitted, it can behave as either. And the Bohr model starts to assume that these electrons are going to orbit in or orbit around the nucleus in those circular patterns, similar to planets around the sun. And it assumes that they can make leaps in quantum level, so leaps from the first shell to the second shell to the third shell, or the first to the third, the first to the fourth. All right, it assumes that it can make these leaps. And so we have to ask ourselves then, if light, typically a wave, can behave like a particle, well then, can particles behave like waves? And at first we want to think to ourselves, well, of course not. Particles are not waves. But it's not quite that simple. A brilliant physicist by the name of Erwin Schrödinger proposed in the early part of the 1900s that a wave function can describe the electron, or that electrons can behave like a wave. And so the wave function squared provides information about the electron's whereabouts in an allowed energy. And so what this turned into is this idea that the electrons aren't going to move in circles around it. They're not going to orbit the nucleus, but they're going to move in almost any direction they want within a certain area of energy. And so the thought in this is, well, can't we just zoom in and take a picture so we know what these things look like, right? We have tons of technology. Can't we just go in there? But the problem is, in order to see something, we have to send light to it and have light come back, right? You can see me now because the screen is shooting out light and it's hitting your eyes. All right, similar to the camera recording, right? Light's hitting off of me and then bouncing into the camera. But the problem with that is that light waves are simply bigger than electrons, or at least so comparably big that when a light wave hits an electron, it will alter the electron. It'll alter its course, which brings us to the Heisenberg uncertainty principle, which says that it's impossible for us to know both the location and the momentum of an electron, or where it is and where it's going. And that's due to light's influence on those electrons. The act of the light hitting the electrons and bouncing back to us alters the direction in which it's traveling. And so we might be able to know where it is, but we don't know where it's going. All right, and so we're not going to get crazy into this, but so the idea is, instead, when we have images of atoms or things you might have seen that say that, they're really a collection of bits of information we have about all the electrons around an atom and kind of all the different places they may have been or the directions they may be going. Which this all brings us to the quantum mechanical model, which really means that the electrons aren't tied to a specific path. Like we said, they don't have to orbit the nucleus in those circle patterns. Instead, their patterns are explained with what's called a probability function, or some really heavy math. I like to call it magic. All right. But what this magic says is that there's these atomic orbitals. So instead of there being these round orbits around the nucleus, there are these atomic orbitals, which we're going to get into and see, which are just a region of space where there's a high probability of finding an electron. And so what this means is when we say there's a high probability of finding an electron, it means that, think about it this way, at 10 o'clock on a Monday, there's a high probability that if your parents were looking for you, you'd be in school, right? Probably in a very specific classroom. But it's not 100%. You could have stayed home for some reason. You could be outside, right, with a class. You could be on a field trip. And so there's a high probability of finding you there, but it's not 100%. And that's how an atomic orbital works. There's a high probability that in this area we can find an electron. But that's it, a high probability. And so we know these as probability clouds or orbitals which have different shapes. And so when we look at the Bohr diagram and we had that first ring, right, n equals 1, and that second ring, n equals 2, and that third ring, n equals 3, all right, each of them can have in there these subshells. The first energy level can have one subshell, the 1s. The second one can have two subshells, the s and the p, the 2s and the 2p. The third can have three, the 3s, the 3p, and the 3d. And so what's happening is as you're going out in energy, you're adding what these are known as subshells. And the subshells can hold a specific amount of electrons. And I know this seems like a lot, but we're going to get into actually seeing what it is. So let's take a look at these subshells. So if we were to look at the subshells, we can see that we also call these orbitals. So there's an s orbital, a p orbital, a d orbital, and an f orbital. And these s orbitals, there's only one, and it's a sphere. The p orbitals, there's now three, and they look like dumbbells. All right, one going along the x-axis, one going along the y-axis, and one going along the z-axis. Then you get into the d orbitals, and these get a little bit different looking. Four of them kind of look like a clover, right? A four-leaf clover, with the one looking a lot weirder. And then we get into the f orbitals, and I'm not even going to begin to try to explain this. We're really not going to talk about this a whole bunch. But what happens is each of these can hold a certain number of electrons, and each of these are a probability cloud. Okay? Now, that all seems complicated, but we're going to get into electron configurations and talk about the actual energy levels and kind of tie it all together in a minute. I just want you to remember the general shape of these and overall what the orbitals look like. As we move into what's called electron configuration, I'm just going to show you a real quick chart on quantum numbers. Now what happens is each of these represents something about that electron. The principal quantum number, n, is that overall shell, right? N equals 1, n equals 2, n equals 3. We saw them in the Bohr diagram. So these are an easy one. You've already seen them. Then there's these angular momentum quantum numbers, and they really talk about the shape. So an s orbital versus a p orbital versus a d orbital, they're the shape. Then you get into magnetic quantum numbers and spin, which kind of talk about, well, does it spin up and down, and what do they look like? We aren't going to get into this in any crazy way now, but I wanted to just give you a little preview that each one of these orbitals has specific quantum numbers associated with it. But what we're really getting into here is electron configurations. And so what electron configurations are just representations of how the electrons are arranged in all those different orbitals. Okay, so do they fall in the S or the P or the D? How do you determine which ones they go into? How do you know? Well, there's 3 rules about it. There's the off-ball principle, the Pauli exclusion principle, and Hund's rule. So let's start at the beginning, the off-ball principle. And so the off-ball principle just says the electrons are going to occupy orbitals of the lowest energy first. And this is a real simple one. Imagine that there's a staircase in front of you, and every so many stairs, there's 1 seat or 2 seats or 3 seats, so on. And I told you, in order to get an A in my chemistry class, all you have to do is go up the staircase and sit in any seat. And then it's, well, which seat are you going to sit in? And if you're being honest with yourself, it's going to be the first one, the lowest one, the one that takes the least effort to find. And that's the off-ball principle. If we look at this chart here, as you go up, it's a higher energy. And so we start on down here at the 1s, the lowest energy orbital. It's going to fill this one first. Then it'll go on and it'll fill the 2s because that's the next highest. And then after the 2s, well, the 2p is there. And then the 3s, and then the 3p. Okay, it's just going to go one by one filling these orbitals. All right, we'll talk about how many electrons and all that with the other rules. This is just saying which orbital, which subshell do we fill first. But then something funky happens right in here. Because what we notice if we look at this is that the 4s subshell is slightly lower in energy than the 3d, which means that the electrons are going to go into the 4s and then the 3d, and then the 4p. And again, this happens with the 5s, where they're going to go to the 5s, then the 4d, then the 5p, and so on and so forth. It keeps kind of going this direction, especially when you get into those S. And we go, well, how can we possibly keep track of this? And so this is the chart here. If we were to write them out, right, in the first subshell, there's only the 1s. Then the second one, there's the 2s and the 2p. And then the 3s, the 3p, the 3d. 4s, 4p, 4d, 4f. And then when we get to 5, there aren't 5 subshells. We don't have a 5G, at least not yet. And so after that, we just are capped at those Fs. All right? Well, what you do is you take a diagonal line and you just draw it down, the 1s, then the 2s, then the 2p into the 3s, then the 3p into the 4s. But now we don't go to the 4p because now we hit the 3d, then the 4p, then the 5s. And so by doing these diagonal lines, you actually can see the order at which you're going to fill these. All right, the 1s, then the 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, and you keep going. And that's just the order at which we're going to put electrons into the orbitals. Okay, so that's the off-ball principle. Now the Pauli exclusion principle, and this is an easy rule. It says for each orbital, there can only be 2 electrons, okay? And the electrons have to spin in opposite directions. We represent this with arrows, and you're going to draw one facing up and one facing down to show that there's 2 electrons in this orbital, one up, one down. So what this means is if we go back to that off-ball principle and our chart, that each one of these squares is capable of holding 2 electrons, one facing up and one facing down, or one spinning up and one spinning down. Each of these squares, so the 1s can hold 2 total electrons. The 2s can hold 2 total electrons. But once you go to the 2p, it can hold 2, 4, 6 electrons. And the 3D, 2, 4, 6, 8, 10. And so we have 10 electrons. All right. So the Pauli exclusion principle simply states that they have to be spinning in opposite directions and 2 per. All right. Well, how you do this is, though, that 1 electron will enter before. So we made a mistake here, guys, and I'm going to correct it here. This is Hund's rule. Bad title. All right. And with Hund's rule, it states how you enter. Okay. And so what happens is when you're entering these orbitals, if there is more than one square in the orbital, so with the 2p, for instance, okay, 1 electron has to enter each of the orbitals in that subshell before a second one can enter. And they have to spin in the same direction. So this doesn't really count for the S's, right? Because they only hold 2. So you enter 1, then you enter the second. But when you get to the P's or the D, all right, what happens is you can't fill this box. You can't do this here, 1 up, 1 down. What you have to do is fill the first box, then, put 1 in the first box, put 1 in the second box, put 1 in the third box. Then you can go back and put the second in, put the second in, put the second in. All right. So it's showing you could do up, 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 or down, 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 but you have to, all right, you have to have them one at a time and spinning the same direction. So not opposite directions or not 2 into 1 orbital. All right. So our 3 rules: off ball, electrons occupy the orbits of lowest energy first. Pauli, 2 electrons can fill each orbital. And Hund's, when they fill them, if there's multiple orbitals within a subshell, they have to do 1 at a time in the same direction. Okay, so now let's get to it. What does this actually look like? How do we do this? So, my turn. We're going to complete the electron configuration of boron, okay? And so in order to know what you do, you go to ptable.com or pull up your periodic table and you look at boron, you say, well, boron with the atomic number 5 is going to have 5 electrons, right? So if we look at it, we know it's going to have 5 electrons. Okay, so first, if you want, we can do our orbital diagram. So we start here at the bottom. Now we have 5 total electrons to place, but we have to start at the bottom, the lowest energy. So we go up, and then we can go down, right? Because there's only 1 box here. So that's 2. We have 3 more to go, right? Up, down. That's 2. We have 1 more to go. And since we're in the 2p, we're going to do up. And that's all 5. Now, I'm always going to draw up first, just how I was taught, but you could equally do down first, then up. All right? And this is the orbital diagram. Now we can do the electron configuration, which really just goes, guys, you listed in order, okay? So we'll put the element symbol, so B, and then we just start off with the orbital. So the 1s orbital, and then in superscript up here, you tell me, well, how many electrons are in that? So in the 1s, there are 2 electrons. All right, well then the next orbital that has electrons in it is the 2s. That also has 2 electrons. Then we have to go to the 2p. And the 2p is just going to have 1 electron. And that right there is our electron configuration. right? It tells us where the electrons are located. There are 2 electrons in the 1s orbital. There are 2 electrons in the 2s orbital and 1 electron in the 2p orbital. All right, let's try another. Now we're going to do carbon. All right, so with carbon, all right, we know that there are 6 electrons now. Okay, so we're going to go over here and we're going to start off, right, with this 1s. We're going to have 1 up, 1 down, 2 electrons. 2s, 1 up, 1 down, another 2, right? Now I have 2 more to draw. So we go to the 2p. So I start here and I do an up, but I can't put it down. I need to go to the other orbital, right? And put another one up. All right, our Pauli exclusion principle. All right, and by that I mean our Hund's rule. Sorry, guys. Our Hund's rule. All right, 1 up, 1 up, and now we have all 6. So when we go to do our electron configuration, carbon is C. In the 1s, we have 2 electrons. In the 2s, we have 2 electrons. In the 2p, we have 2 electrons. And that is our electron configuration. Okay, so now the last one we're going to have you give it a try. All right, you give it a try. We want you to complete the orbital diagrams, electron configurations for nitrogen and oxygen. All right, go ahead and give this one a try. Pause the video, give it a try. Okay, so now you should have it back. So what we're going to know is that with oxygen, we have 8, and with nitrogen, we have 7. So let's try these things out, right? So let's do nitrogen first because it has 7, right? And then we can always add that one more for oxygen. So for nitrogen, we could do 1, 2, right? We got 5 more to go. 1, 2, 3 more to go. And so then we just have 1, 2, 3, and we stop there. All right, there it is. Okay, 1, 2, 3, 4, 5, 6, 7. So then if we wanted to do nitrogen, we'd say, well, we have the 1s with 2, the 2s with 2, and the 2p with 3. All right, so now if it's oxygen, we just had to do 1 more. So let's not erase all this. Let's add 1 more. Now, where do we add it, right? Could we have up, up, up? Well, now we need to add a down because now we finally have a 4th electron. We got to add 1 more. And so then with oxygen, guys, very similar. 1s2, 2s2, 2p4. And that is the basics of electron configuration.